Hello everyone, my name is Miguel Salin. I started working on Landlock some time ago and now it is finally a Linux mainline. At first it started as a personal project motivated by personal needs. I wanted to take control of my own data on my Linux workstation. I then continued this work with my previous employer, the French National Cybersecurity Agency, and now with Microsoft. This talk is a complementary to the one I gave yesterday at the Open Source Summit, which was named Sandboxing Application with Landlock. But this time, I'll focus on the kernel side. We'll see how Landlock works underneath and what are the constraints of an unprivileged monetary access control system. But first, let's see what we'll try to solve here. This drawing illustrates the reason why I started Landlock. It says, if someone steals my laptop while I'm logged in, they can read my mail, take my money, and impersonate me to my friends, but at least they can't install drivers without my permission. Here, the problem is not to steal a laptop, but to compromise an application, which will then be able to access user data. This talk first explains the goal of Landlock and the related consequences. We'll see how to use it, a bit of a story that led to the current design. It will then explain the kernel implementation constraint and the potential limits of the kernel in future features. But first, let's see what is really sandboxing. Sandboxing can be used for different meanings, but in this talk it is used as a security approach, not a binary state, to isolate a software component from the rest of the system. We suppose that the running system is trusted and not compromised at an early stage. However, once started, it can be attacked, and without compromising the trusted computing base, illegal access to restricted data could happen because of compromised application. Indeed, an inaccused and trusted process can become malicious during its lifetime. The threat models are first to protect from vulnerable code maintained by the application developer, but also to protect from malicious or vulnerable code from third-party code. And finally, the threat model can be defined by the developers as it fits best. But what is Landlock? Landlock is the first monetary access control system available to unprivileged recipients since Linux 5.13. The idea is to restrict ambient rights according to the kernel semantic, for example, global system accesses, for a set of processes, because this cannot be done with seccomp. Landlock enables to develop built-in application sandboxing to protect against either exploitable bugs in trusted applications, or to protect against untrusted applications thanks to sandbox managers. Contrary to other monetary access control systems, like SLNX, Alphamore, SMAC, or Tomayo, Landlock empowers any process, including unprivileged ones, to securely restrict themselves. From the user space point of view, Landlock offers 3 system calls. Each one of them is designed to do a specific action. They can be seen as a builder pattern. An initial rule set is created thanks to the Landlock create rule set syscall. This rule set is then usable thanks to a specific file descriptor that can be passed to the Landlock add rule syscall. And finally, once the rule set is ready, this rule set can be enforced and restrict the calling process thanks to the Landlock restrict self syscall. Landlock enables to protect user data from unauthorized access or disclosure by making it possible for threads and their future children to only allow access to a set of file hierarchies. The access right, are execute, read, or write to a file, list a directory or remove files, or create files according to the type. Here is an example in C, but we can do the same thanks to high-level libraries for Go and Rust. First, we need to create a rule set attribute that will define the rule set and will contain a set of access rights. All these actions will be denied by default except if a rule inside this rule set allowed this action. Then we need to pass this rule set attribute to the Landlock create rule set syscall, and if the call succeeds, then we get a rule set file descriptor. The second step is to add rules to this rule set. To define a rule, we can create a path beneath attribute, which contain a set of access rights. Then we can open a path, which will then be identified thanks to another field from this path beneath struct. We can then, thanks to the rule set file descriptor, pass this struct, this row, to the Landlock as rule. If the call succeeds, the rule set gain this new rule. The final step is to enforce the rule set. Once all rules are added to the rule set, we can then pledge to the kernel that the current thread will not gain new privileges, which can be done thanks to SYD binaries, for example. Then we pass the rule set file descriptor to the Landlock restrict self syscall. And if the call succeeds, the calling thread will be restricted by the rule set. I started working on Landlock 5 years ago. At first, it was a proof of concept to extend seccomp, which was called seccomp object, and it was using the seccomp syscall, and it was a bit hacky, but the idea was to be able to filter not only row arguments, but kernel objects as well. But then I switched to the LSM framework, so not at the syscall layer, but really more close to the kernel semantic. And I also used eBPF and cgroups. A major step after that was to create a new BPF helper, which was able to identify file path. After that, it was mainly to shrink patches to make the patch set minimal. The major event happened in 2020, where we moved entirely eBPF and replaced the seccomp syscall used with a new dedicated syscall, which was in fact a multiplexer. The next step was then to remove or replace this multiplexer syscall with 3 dedicated syscalls, which are now Landlock create rule set, Landlock add rule, and Landlock restrict self. And finally, after some iterations, in 2021, the 34th version was merged in mainline for Linux 5.13. So, why no more eBPF? Because of seccomp BPF, on which the first version of Landlock was based on, I then used eBPF as a way to define security policy which could be updated on the fly, thanks to eBPF maps, and evolves over time. The main goal of Landlock was and still is to bring sandboxing features to all users, which means to have an unprivileged access control system. eBPF is very powerful, and I proved with previous version of Landlock that it is possible to implement an access control with it. However, a programmatic access control does not fit well with unprivileged principles. Indeed, eBPF can also be leveraged by attackers against the kernel, which is now why eBPF is not meant to be used by unprivileged users anymore. But also programmable interfaces with I/O, for example eBPF map, can lead to side channel attacks against other programs, which is an issue for unprivileged access control. It is also not possible to efficiently compose loaded programs but only to chain them, which is done for seccomp DPF, for example. But that is not enough to get an efficient access control based on the file system. But still, this work contributed to bootstrap the BPF LSM, previously called the kernel runtime security instrumentation, which then gained an extra feature thanks to BTF and make it much more powerful. Now let's see the priorities and guiding principles for Landlock. First, we need to make sure that we don't weaken the system security by adding new features. When modifying the links kernel, it means that these new features are potentially entry points for attacks against the kernel and all resources it controls access to. Second, only sandbox processes shall be accounted for the sandbox, and we should limit the use of non-user space accounting, which means the kernel. This includes access check time and allocated memory. Third, we need to protect unsandboxed processes from sandbox processes. Indeed, sandboxing is meant to isolate potentially compromised processes and then limit the malicious impact on other processes. Being able to manipulate or impersonate other processes may also be used as a pre-escalation, for example, the confused deputy attack. And finally, of course, sandboxing should be useful to limit access to data. Now let's see the implementation constraints of an unprivileged access control system. First, this needs to be useful for multiple and different applications, which means independent but innocuous and composable security policies must be guaranteed. We also need to prevent bypass through other processes and to follow the principle of least privilege. And finally, to limit the kernel attack surface, for example, by using simple policy degradation, but not bytecode. How do we compose security policies? First, at the system level, there is other access control systems, and that is done thanks mainly to the LSM stacking work. The other part is specific to Landlock. It is to compose all sandbox policies in an efficient way. From the kernel point of view, Landlock is implemented as a Linux security module, an LSM, which means that it relies on a set of access control hooks wired deep in multiple kernel subsystems. In practice, to be useful and used, Landlock needed to be usable as a stackable LSM. Indeed, for security in-depth approach, we should not replace other security mechanisms, but add more security layers on top of them. Landlock has been a recognized motivation for the development of LSM stacking. By the way, thank you, Casey. Each LSM can register a set of hooks for a set of actions, which enable to check access, for example, when opening a file, sending a network packet, doing an NECTL, and so on. And each LSM can also now register for blob sizes for a set of kernel object types, which are used to tie specific data to kernel objects, for example, inode, files, socket, and so on. The kernel denies an action when the first hook call returns an error. These are sequential checks. Thanks to the implemented constraint, an important advantage of Landlock is the ability to compose security policies. Indeed, because each application can define its own security policy, the kernel must merge them in a safe way. From a user point of view, this must behave like a stack of scoped sibling or nested policies. However, for performance reasons, This composition cannot be simply implemented as a stack of policies. Moreover, dealing with complex data structures implies dealing with multiple underlying mechanisms like namespaces, mount points, overlays, and special file systems. And this means also that we need to handle a hierarchy of policies. The sandbox can only drop more accesses. Sandbox policy composition applies to file identification and brings constraints. First, we cannot use extended attributes on files because we must handle multiple policies, and that will mean to add a lot of data to these extended attributes. But we also must enable to embed policies, which means ephemeral identification, because application can be updated and this corresponding identification must follow these updates. And we should be able to deal with read-only files. The second thing is that we cannot directly use absolute path because we may not have access to the real root. We may be in a container, in a file system namespace, and we must not be a way to bypass other access control systems, which, for example, could be sidechain attacks to infer where we are in the global file system. So, how does work the file identification for Landlock? Well, we first use inode tagging. Access rights are tied to inodes by user space thanks to open file descriptors and a new system called the Landlock add rule. All access rights for the same inode are stored inline in a dedicated kernel struct, kind of a tag, including a flexible array, which enables to have efficient lookup for specific inode. And then lifetime of such tags depends on associated sandbox domain lifetimes and underlying superblock lifetimes, thanks to a new LSM hook that we added, the security SB delete. The second part is to check file hierarchy. When requesting access to a file, we walk through all parent files until all domains have been checked or the root is reached. Now let's see an example. Let's say there is a shell application that wants to sandbox a user station. This case is the first layer of sandboxing, and there is 7 rules. There's one to allow execution of other applications, one to read the configuration, and other access rules to enable read or write for specific directories, including the user home directory. Now let's say a user in this session wants to launch an application that also sandboxes itself. This application will require access to maybe libraries, configurations, and cache files, configuration files, and let's say it is a picture viewer, the picture directory, in a read-only way. And now let's say that the picture parser can also sandbox itself to restrict the attack surface. In this case, the parser inside the picture application, we only have access to the cache and the selected picture, which is in this case /home/user/pictures/cool.jpg. So this is the third layer. Now let's see how the kernel checks if a specific access to a file is allowed or denied. For example, this cool picture. First, it checks the first inode, which is the file, and in this case, the third layer allowed access to this file. So it's okay if all other layers also allowed access to this file with a specific action, which is here a read-only action. So the kernel walked to the parent directory, here the pictures one, and it checked that the second layer also allow access in a read-only way to this file hierarchy. The kernel then continue to walk to the parent directory and find that the parent directory, the /home/user, is also allowed to be accessed in a read way. So the kernel knows that all three layers allowed this action on this specific path. So the kernel don't need to continue the walk to the parent directories, and the action is allowed. Now let's look at another angle, the policies hierarchy. Let's say there's the first process P1 that can create a new child, P2. All of these processes are sandboxed. But now P1 wants to sandbox itself, so create new sandbox. In this case, you can see that P2 is not sandboxed because, well, it existed before P1. So the process hierarchy is not the same as the sandbox hierarchy. Then P2 wants to create a new process, P3, which inherits the P1 sandbox. But P3 can also create its own sandbox domain. And this doesn't mean that it will escape the P1 sandbox, but it will gain an additional sandbox. Then if P3 creates a new process, P4, this P4 process will automatically inherit the P1 sandbox domain and the P3 sandbox domains. So all these protections will apply to P3 and P4. Because Landlock sandboxes can be nested, the kernel must make sure that the sandbox boundaries cannot be crossed in a way that will lead to a privilege escalation. To make this simple and effective, Landlock checks sandbox hierarchies when a sandboxed process requests access to a process from another sandbox, which means through ptrace, which is a debug feature. Only a process pertaining to a parent sandbox, or no sandbox at all, can access processes from a child sandbox, which means with same or less privileges. In this example, P2 can ptrace P1, P3, and P4. P1 can ptrace P3 and P4, but not P2. And P3 and P4 can ptrace each other, but not P1 nor P2. It also applies to special POCFS files. A new access control mechanism should come with guarantees. We use the K-self-test harness framework, which comes from seccomp, and made it more generally available to other users. We wrote kernel case tests to check the different access control types and make sure that all the relevant kernel code is covered. As a result, there are twice as many lines of test code as lines of kernel code. The code not covered only deals with internal kernel errors, for example, memory allocation, and race conditions. Now let's see some other way to test the kernel fuzing. T-Scholar is an unsupervised, coverage-guided kernel fuzzer. More than just carefully writing and reviewing the code, we extended the syscaller further to get a decent and meaningful code coverage of Landlock. As a proof of effectiveness, it led to a bug discovery, independently fixed in a past version. We added Landlock system calls, extended some specific system calls related to file system or btrace, added tests to help it discover specific Landlock kernel code, and reach good coverage, which is really hard to get better. And finally, we check that you can indeed find bugs. Thanks, Dimitri, for your help. The current state of Landlock in mainline is a minimum viable product. The idea was to upstream the core part of Landlock that make it both useful but still simple as much as possible. There is then file system limitations to avoid potential policy bypass because of policy compositions. In a sandbox, file replanting is denied, which means renaming or linking a file to a different parent directory. Also, file system topology changes are denied, for example, doing mount points or changing the root directory with pivot root. However, the shoot syscall is still allowed. This is still okay for generic read-only environments. Because of the unprivileged approach, there is design limitations. Unprivileged access control cannot restrict anything. For example, not all processes and not the kernel. Then the hierarchy of sandboxes. Current LSM hooks need to be updated to bring more access control types to Landlock. For example, there's a lot of inode-based hooks, but not so much path-based hooks, which are used by Landlock. However, to fill the current limitations, TechBPF can help to complete a sandbox. Let's see the kernel side roadmap. In the short term, that is to improve kernel performance for the kernel features and to add the ability to change the parent directory of files like we saw before. In the medium term, we want to add audit features to ease debugging, to extend file system access control types to address the kernel limitations, and to add the ability to follow a deny listing approach, which is required for some use cases. In the long term, we like to add minimal network access control types to build application firewalls, and to add the ability to create file scheduler capabilities compatible with FreeBSD's capsicum. Okay, let's wrap up. Landlock is designed to be inclusive, which means it is an unprivileged mandatory access control system available to any process and any user, and safe to use from the design to the implementation with a lot of tests. Any process should be able to protect user data or even system data, considering some implementation constraints. In a nutshell, Landlock is a minimal but extensible interface to create sandboxes. Please feel free to ask any questions on the chat or on the mailing list, and you can take a look at the website to find more information. Thank you.